Dear students, welcome to my channel. Topic of this video is image compression. This is the second video on this topic. In this video, I am going to discuss various types of redundancy present in an image, mainly coding, interpixel and psychovisual. Now let us start. Redundancies. Two-dimensional intensity array, that is nothing but image, suffer from three principal types of data redundancies, which are as below. First is coding redundancy. Some gray levels are more common than others. Interpixel redundancy, the similar gray level covers larger areas. And third, psychovisual redundancy, the eye can resolve only 32 gray levels locally. Compression attempts to reduce one or more of these redundancies type. First is coding redundancy. Pictures are made up of tiny squares called pixels, and each pixel has intensity. Each image is represented by a particular bits per pixel, that is nothing but BPP. For example, 8 BPP, that is grayscale image. Each image needs 8 bits and they can represent intensities or colors from 0 to 255. However, most of the time we have very few intensity variation in an image, but still we encode the image using the fixed 8 bits, that is nothing but fixed length encoding. Coding redundancy is present when very few intensities are present in an image and image is encoded using the fixed, that is nothing but the 8-bit encoding. Now we'll see with the example. This happens when we use the fixed byte to represent the intensity in an image, even if some intensities are frequent and some intensities are infrequent or rare in nature. It means same length code to encode every pixel in an image regardless of how often it appears. We can improve coding efficiency by using shorter codes for frequently occurring intensity and longer codes for rarely occurring intensities in an image. Now see the example. The image size having 10 into 100, that is 10 rows, and in each row 100 pixels are there. So total 1000 pixels are there, and in that image can represent the color from 0 to 55, that is 256, but only 5 colors are present in an image, and which is represented by intensity 1 to intensity 5. Now here if we see the variation, then intensity 1 and intensity 2 are dominant, that is they are frequently occurring, but 3 is mid level and 4, 5 are rarely occurring the intensities in an image. But if we apply the fixed length encoding, then we are encoding each pixel with the 8 bits, that is nothing but 1 byte. So size of the image in the form of bit is 1000 into 8 is equal to 8000 bits. But if we apply the variable length encoding, then we can encode each pixel with a different bits. After applying the Huffman encoding, we can get the variable length encoding. Now after applying the variable length encoding, I get, that is intensity 1 can be represented with 1 bit, intensity 2 can be represented with 2 bits, intensity 3 with 3 bits, and intensity 4 and 5 with the 4 bits respectively. Then if we use variable length code to encode each intensity, then to encode this 500 pixel we are representing with only 1 bit, next 300 pixel we are representing with 2, 100 with 3, and 4 and 5 with the that is intensity 4 and 5 with the 4 bits. So total 1800 bits are there. So original size is 8000 bits and the compressed size is 1800 bits. If we calculate the coding compression ratio, it will becomes 4.44. That is the first image contains the coding redundancy, that is it's larger, that is 4.44 larger than the compressed image, and we are getting the data redundancy as a 77%, that is data can be redundant in an image. This is just represented visually. So image is having 10 into 100, total 1000 pixels are there. So for simplicity I have represented each pixel in a continuous manner, so we can get the nature of this. But actually the not necessary that pixel should be into the continuous, and this is nothing but the histogram. And here when we see the histogram, we can see that the image intensity 1 and intensity 2 are the frequently occurring, and intensity 4 and 5 are rarely occurring. So here based on their occurrences we are assigning the bits. The pixel which are occurring frequently we are assigning the fewer codes. Now we can see that how much that average bits are required to represent that image. Now probability of RK is equal to NK by N, and L average is equal to summation from K0 to L minus 1 into length of RK into probability of RK. Now we will see with the example. where n is nothing but the total number of pixels in an image, rk is nothing but total number of pixels in gray level. Now here 5 k gray levels are there, that is intensity 1 to intensity 5. K is particular gray level, k equal to 0 to L minus 1. L is nothing but total number of gray levels present in an image. Now here intensity values are 500, 150, 200, 250, and frequencies are 500, 300, 100, 75, 250, 75, 25. So if we add this, we are getting the 100 values. So for simplicity, I have given that colors, and this is nothing but the frequencies they are occurring with an image. Now if we calculate the probability, now we are calculating the probability, and here we can find out that that is 50% pixels are of color having the intensity value 50. So therefore probability is 0.5. So we are dividing 500 by 1000, we will get 0.5. 300 by 1000 we are get 0.3. Then 100 by 1000 we get 0.1, and for this we are getting 0.075 and 0.025. If we add this probability, we will get the value 1. Now if we use the fixed length encoding, then we require to apply the formula. The formula is nothing but length of rk into probability of rk. Now here in fixed length encoding, we are using the fixed number of bits, that is nothing but 8. So everywhere here it is multiplied by 8. Then 0.5 into 8, 0.3 into 8, 0.1 into 8, that is nothing but probability with the whatever that bits we are used for encoding. So we are getting this value, and when we add all this value, we are getting the 8. So average 8 bits are required to represent each pixel. But if we use the variable length encoding, our answer is different. So this is nothing but the probabilities. And now for the first pixel, we are using only 1 bits. For second also we are using 2 bits. For third 3, and for 4 and 5th we are using the 4 bits. And if we do these operations and calculations, we are getting the 1.8. So averagely 1.8, or it is close to the, or approximated to 2, that is only 2 bits are required to represent the each pixel. So this is nothing but we are achieving the compression by reducing the coding redundancy. If gray levels of an image are coded using more symbols than absolutely necessary, it is said to contain coding redundancy. Variable length coding is very powerful and frequently applied by assigning the fewer bits to the more probable symbols, and which achieves the compression. It is not just for images, character strings too. Zip, gzip used all form of variable length encoding. Drawback of variable length encoding: equally probable symbols are there, then we can't get much more after compressing, and generally no gain, then don't encode. So first generally we see the entropy of the image, and based on that we can get the idea whether coding redundancy is present in an image, and if present, then only we apply. Otherwise we don't have any gain if we apply the variable length encoding. Second is interpixel redundancy. It is a redundancy corresponding to the statistical dependencies among pixels, especially between the neighboring pixel. Interpixel redundancy implies that pixel values are correlated. For example, if you take a particular area in an image, and where the gray levels are changing very smoothly, that is there is no drastic change, so at that time we can say that in that particular portion of the image interpixel redundancy is present. That is, pixel value can be reasonably predicted by its neighbor. So two types of type are there, that is in an image spatial redundancy is there, and in videos temporal or interframe redundancy is there. Spatial redundancy, which is present in an image, neighboring squares often have similar colors or intensity values. This means information about a pixel is represented in its neighboring square. This repetition is called spatial redundancy. Temporal redundancy, which is present in videos. Videos are like flip books with many still images. Consecutive frames often show the same scene with slight changes. This repetition of information across frames is called temporal redundancy. In simpler terms, both image and videos are waste space by storing the same information at multiple places. Now this is nothing but the two types of redundancies are present, that is it may be vertical and it may be horizontal. So generally when in compression, both type of redundancies takes into the consideration, that is across vertical and across horizontal also. To reduce the redundancy associated with spatially and temporary correlated pixel, that is nothing but interpixel redundancies, an image intensity array must be transformed into a more efficiently but visually non-visual representation. So when we encode this interpixel redundancy, at that time we are getting the non-visual representation. For example, run length or difference between the adjacent pixel can be used, and transformation of this type is called mapping. A mapping is said to be reversible if the pixels of the original image can be reconstructed without error from the transformed dataset. Otherwise, the mapping is irreversible. So when we are using the lossless compression, our mapping is reversible, and when we are using lossy compression, our mapping is irreversible. Coding method, so we can use either run length coding or we can use a difference coding. So we will see first the run length coding. Every code word is made up of pair, where G is the gray level and L is the number of pixel with that gray level. So here we can see that, so generally in an image, the variety types of directions are there in which we can encode. We can encode either each row, or we can encode like this, that is we will go from left to right, and after that we will from the second we can start from the right to left, because by this way we can capture the horizontal redundancy as well as the vertical redundancy. So in this way also we can go for the run length encoding. So this is all depend on implementation, whether we want to go for the horizontal or we want to take horizontal then vertical and then again horizontal way. So here now see, for this image only 2 rows are taken. So now here we can use the run length encoding. So run length encoding is useful only when there is a runs of the particular intensity, otherwise it turns into the negative compression. Now here 56 is repeated for 3 times, 82 is repeated for 3 times, 81 is repeated for 1 times, 80 is, now we are going in this direction, 80 is represented for 4 times, and 56 is represented by 5 times. The code is calculated row by row. Very efficient coding for binary data. Important to know the position and the image dimension must be stored with the encoded image. It is used in the fax machine. So at the time of decoding, what we are doing, we are storing the information that what is the size of the image. So at the time of decoding, so this is nothing but the non-visual representation, and this is visual representation. So this is nothing but original image which is in decompressed format, and when we apply the run length encoding, it compressed and it converts into this non-visual format. So when we want to decompress this encoded form, then we are taking into the consideration what is the size of the image. So at the time of decoding, we are replicating 56 for 3 times, then 82 for 3 times, then 83 for 1 times, and we know the size of the image is 8. So that is the horizontal 8 pixels are there, so we are going like this way. So 80 is again 4 times, so we are going in this way. So in this way the image is decompressed again. Now see this image. So this is 8 by 8 image. Now here we are going not by this way but row wise, so it's all depend on our implementation. Now here we can see that when we are going row by row and only 8 pixel or at most 8 pixels are present in that, then we can see that any particular pixel can be present for maximum 8 times. So here the count of runs is very important. So when the pixel is present for 1 time, minimum is 1 and maximum is 8. So when the pixel is present for 1 time, we are using this symbol. When the pixel is present for 2 times, we are using this symbol, and maximum value of pixel can be representation is 111. Here there is no need to take the 0, because when 0 that the pixel is not present, we are not encoding that particular symbol. So here for the first row, that 0 is repeated 8 times. So 0 is repeated 8 times, it is encoded like 0 is represented with 000 and 8 is represented with this 111. So 111. Next is 0 is repeated for 2 times, 1 is repeated for 2 times, 2 is repeated for 1 times, and 3 is repeated for 3 times. So 0, that is nothing but 000. For 2 we are using that 001. So in this way we are representing like this. So in this way the image can be compressed or encoded by using the run length encoding. So original image requires 3 bits per pixel, that is nothing but 192 bits, and in the compressed image, so there are 29 runs are there, and for each run which we require 3 plus 3 6 bits, that is nothing but first bit is to store which pixel, and third is nothing but next pixel is the, or next bit is nothing but how many times it is repeated. So for 3 bits the pixel value, and the next 3 bits is nothing but their run. So 6 bits per run is required. So total size after compression we require only 174 bits. So this is nothing but by encoding or by removing or by reducing the interpixel redundancy, we again get the compression. Now one way is that either we can use the run length encoding or we can go for the difference coding. So in difference coding we are using second minus first. So for example, this is the one row considered. Now here we are keeping the first as it is. Now for the second we can subtract from the first, because the pixel regions are very similar in nature, so we are getting very difference very small. So 56 minus 56 is 0, 56 minus 56 is 0. So we are subtracting the previous value. 82 minus 56 is 26, 82 minus 82 is 0, 83 minus 82 is 1, and in this way we are making the or we are capturing the interpixel redundancy. Now here, if we want to go for lossless compression, we are keeping this difference as it is. But when we are going for lossy compression, at that time we can see that this 0, 1 and minus 3, they are having a very small difference. They are very similar to each other. So for simplicity or to get the continuous runs, what we can do, we can make this 1 as 0 and minus 3 as 0. That is a permanent change. So that becomes a lossy compression technique. So in this way, either to capture the interpixel redundancy, variety types of methods are there, but we can go for the run length and difference encoding. Now this is another example. This is original image and this is nothing but the difference image. So here again it is taken as by this way, that is row, then after that left to right and then again right to left. So in this way it is encoded. So first pixel as it is, second pixel is nothing but 8 minus 9, 7 minus 8. In this way image is constructed. So if we can see that only 9 and 7 values are dominant, otherwise all differences, even minus 5 is drastic difference is there. If we want to go for lossy compression and we don't want the differences up to plus 5 or minus 5, then we will all make it 0. So by that way we are getting more continuous runs, and when we go for the second time of encoding, we will get the more compression. So in this way we are either go for lossy or lossless. So when we are going for lossy, we are here after first difference we are permanently changing their values, and if you go for lossless compression, we are keeping as it is. Third type of redundancy is psychovisual redundancy. Now see, this is nothing but the two images and we require to find out the difference between the two images. So when we observe the image carefully, then only we are able to find out the difference between the two images, because our eye perceives the entire image. So when we see these images, generally first observation is that the images are very similar, but when we find out the differences, when we are looking the each portion of the image in detail, then we can find out the differences. For example, here 4 trees are there, here 3 trees are there. So this is nothing but what psychovisual redundancy. As a eye, we can perceive the entire image. So initially we found that two images are very same. So that is nothing but what, if the particular pixel is not discriminating to us, then why to encode? So see, this is the image. Here the pixel values are varies between 125 to 131. So even the pixel values are different, but for our eye they are looking at the same value. So if we draw the histogram of this, we are getting this values, that is all pixels are between 125 to 131. But here, as our eye can't discriminate between 125 to 126, 127, 131, so why to use different values? So better we can represent all this image using either all 25 or any number between 125 to 131. So if we represent this image by only one pixel value, we will get the continuous runs and we can compress more easily. But here it becomes the lossy compression, because instead of keeping the separate values, we are making the one value. So its elimination is possible because the information itself is not essential for the normal visual processing and intended use of the image. Because its omission results in loss of quantitative information, its removal is commonly referred as a quantization. That is nothing but this is the one of the important step in lossy compression. This terminology is consistent with the normal use of the word, which generally means the mapping of broad range of input values to limited number of output values. Because information is lost, quantization is an irreversible operation. So why we are giving concentration to the psychovisual redundancy? Because our eye does not respond with equal sensitivity to all visual information. Some information has less relative importance than other information. This information is said to be psychovisually redundant. It can be limited without significantly impairing the visual quality. Unlike coding and interpixel redundancy, psychovisual redundancy is associated with real or quantifiable visual information. It is possible only because the elimination of this does not affect the visual process, but we lose original information, that is nothing but the quantifiable information. Thus, this type of reduction is called quantification and it is the lossy. So, this is all about the redundancies present in an image, and in compression we generally try to reduce this one or more redundancy based on the presence. Thank you.